Okay, so let's start. So hello everyone, welcome to today's webinar organized by UNESCO Chair in Disaster Reduction and Resilience Engineering. Thank you all for joining us today. Before we begin, I would like to take a moment to introduce our next webinar first, which is about resilient and sustainable schools, a life cycle and multi-objective approach for National School Infrastructure Plan, which will be organized on the 8th of May. So please follow our website, social media, and of course, we also send you the registration links by email. So please keep in mind and as well your calendar. So let's move back to our today's webinar. We are very honored to have two guest speakers from TRAP Technology Inc., Sinan and Adam, to give us presentations on earthquake loss and modeling for reinsurance, which I believe will be quite insightful. Firstly, let me introduce our speakers. Our first speaker, Sinan Akar, is currently the head earthquake catastrophe modeler at TRAP Technology Inc., the research, development, and technology company of Turk Reassurance Inc. He served as a full-time professor at the Middle East Technical University and Bogazici University between 2003 and 2021. Sinan has been the team member and technical integrator of ground motion characterization of shock level 2 and 3 nuclear power plant seismic hazard project in the US, Europe, Turkey, and Kingdom of Saudi Arabia. He also acted as the principal investigator of the revision of national seismic hazard maps and the revision of the compulsory earthquake premiums for Turkish catastrophe insurance pool. He is a member of the board directors in the International Earthquake Engineering Association, the Turkish Earthquake Foundation, and editorial board member of Journal of Earthquake Engineering. Our next speaker, Adam Karaboston, is the general manager of TRAP Technology Inc. He brings over 18 years of experience in insurance, reinsurance, and project management. He started his career in 2006 and Anadolu Sigorta as an assistant internal auditor and climbed the ranks to become a project manager. Adam has held significant leadership roles, including deputy general manager at Turk Reassurance, where she was responsible for IT, HR, claims, CAD modeling, legal, and risk engineering. In 2023, he joined TRAP as a general manager, steering the company with his expertise in business solutions management, IT audit, and compliance. Adam holds certifications as a project management professional, certified information systems auditor, and ITIL V3 Foundation certificate. He is fluent in both Turkish and English and is a graduate of Middle East Technical University. So before we get started, here's a quick note for you all. You are all welcome to submit your questions at any time during the webinar into our Q&A chat box. And we will have a dedicated session following the presentations to have our guest speakers answer the questions as many as possible. So without further ado, I will hand it over to our first speaker, Sinan. So please, the floor is yours.
Thank you very much, Liasheng, for this very nice introduction. So I'll be sharing my screen to start talking about the topic that we prepared together with Erdem. Can you see my screen now?
Yes.
All right. Okay, good then. So as Liasheng has already indicated, we will be talking on the earthquake loss modeling for insurance and reinsurance. I will be presenting about the fundamentals, the theoretical aspects of earthquake loss modeling, and then I will be talking on the main model variables, and their effect on the loss, on the calculated loss, by saying that I'll be explaining or presenting our observations based on building location uncertainty, poor representation of building properties, variability in site conditions, variability in damageability characteristics of buildings. In other words, the vulnerability, building vulnerabilities, as well as the ground motion and damage correlation. And meanwhile, Erdem will be focusing more on the implementation aspects or part of the earthquake loss modeling. What do we understand as insurance and reinsurance industry about earthquake loss modeling? All right, so the first part of my presentation is going to be about the fundamentals of earthquake loss modeling. I will be describing the important components of the earthquake loss modeling first. Before going into the details of earthquake loss modeling, I'll give a sort of generic definition of catastrophe risk modeling. Earthquake is a natural catastrophic event, so it's a part of catastrophe risk modeling. So essentially, catastrophe risk modeling, or as abbreviation CAT modeling, is used to estimate the social and financial impacts caused by either the natural catastrophes, like the earthquakes, hurricanes, tornadoes, and floods, or man-made disasters, such as terrorism, extreme casualty events, and cyber threat, that can jeopardize the well-being of human beings, both in social and financial terms. So the CAT modeling, as I'm showing here, different types of catastrophic events, phenomena, is widely used by insurers and reinsurers to manage their risk and pay the claims against catastrophic events. So for the insurance part, the manager of the company or the management of the insurance company would like to know the level of risks that they are taking for a catastrophic event for their payouts. And then once they have a quality information about this risk, they would give a decision on what part of that risk should be transferred to reinsurance companies. And then the management of reinsurance companies actually would like to know what is going to be their risk if they take over some of the risk from the insurance companies in terms of payouts or financing their burden against a specific catastrophic event. So essentially, the CAT modeling is entirely probability-based because we are dealing with, firstly, infrequent events, which means you have to sort of simulate those events from the past learnings, from the past experience. Then you will always have insufficient information about the exposure, the location of the risks in the exposure, the type of the structural systems in the exposure, the properties of the exposure, of the risks in the exposure. Those kinds of that kind of critical information will not be complete in many cases. So you have to make smart assumptions and smart assumptions, as well as you have to come up with distributions, probability distributions, to sort of close that gap in terms of knowledge. Then again, because of the nature of the catastrophic phenomena events, there is a lot of uncertainty in terms of unknown information for vulnerabilities, and then also the there is a lot of sort of variability, random variability by the nature of the catastrophic event. By saying the unknown, epistemic uncertainty in the vulnerabilities, which is one of the major components of the risk modeling or loss modeling. Because of the insufficient information in the exposure, you have to make a lot of you have to address that kind of missing information, as well as the structural behavior of the exposure by including uncertainties in the vulnerability models. Vulnerability models essentially will give you the likely loss given a specific intensity metric of the catastrophic event, which is in this case the earthquakes. Now, in terms of intensity metric that you're going to compute from the hazard, again, in our case, the earthquakes, there is a lot of uncertainty or variability because of the random nature of the earthquake event. So in this case, for example, I'm giving you here a specific case for the variation of ground motion intensity metric as a function of distance. So as you see, for a given specific magnitude range, say for earthquakes of magnitude between 5 and 5.5 or 5.5 to 5.6 and so forth, the variation of ground motion intensity metric like peak ground acceleration, velocity, or spectral acceleration at a given vibration period, you will note a lot of variation as a function of distance. And then you have to essentially address this variability, which comes from the nature of the event, by considering the aleatory variability. So that's why essentially the CAT modeling is probability based. Now, to sum up, we're going to have a modeling perspective completely relying on probability, and because we're predicting the frequency of future events that are likely to affect the portfolio size, and we don't have too much of information, or we have limited information about the frequency of future events, so we have to use distributions in this case, and then we have to predict the likely locations of these future events again on the seismic sources, and which means again this is a lack of information, and we have to use distributions for this case, and also we have to make an estimation of loss for different exceedance probabilities, and then for insurance and reinsurance portfolios, insured and reinsured portfolios, and essentially because of the unknowns in the ground motion behavior and because of the unknowns in structural behavior, we have to consider the probability distributions. All right. What are the main outputs of CAT models? Now, I will be talking on the way how we compute them and what they are used for. And then, as I told you, Erdem will be explaining more how they are actually understood by the insurance and reinsurance industry in the professional life. So essentially, the main outputs of CAT models, firstly, the exceedance probability curves, abbreviated by EP curves. And there are two types of exceedance probability curves, the occurrence exceedance probability and aggregate exceedance probability. In the next coming slides, I will be explaining on these terms. And then from exceedance probability curves, you can compute the average annual losses, the probable maximum losses, and also maybe a very important parameter, the tail value at risk. And then by making use of these outputs, you can give sort of decisions on, or you can make use of them for rate making, portfolio management, underwriting, risk, and then for underwriting, and before underwriting, the risk selection, loss mitigation strategies, allocation of cost of capital, cost of reinsurance and risk transfer analysis, enterprise risk management, as well as financial and capital adequacy analysis. I'm not going to go over them one by one because of the time limitations, but each one of these, items here constitute an important part in the decision making in insurance and reinsurance industry. The managerial staff, as well as the experts in insurance and insurance industry, by making use of these outputs, essentially give decisions for each one of these components indicated here. All right. Now, when you start establishing a CAT model, there are some, fundamental components. Firstly, you have to know about the exposure. By knowing about the exposure, you have to know the geolocation of the exposure, the coverage type in the exposure. So in the exposure in insurance and reinsurance exposures, we have coverages for structural damage, content damage, or business interruption based on the damage inflicted by earthquakes. And then we need other information about the structural systems, like the construction material, main structural system, the year built, number of stories, site condition, the occupancy type, and also information about the content, which is the type of the content, location in the location of the content in the sheltering structure, and so forth. As I told you, if you have unknowns, missing information in these items, then you have to reflect that kind of unknown in your vulnerability model. Now, after exposure, you have to consider the hazard component. The hazard component consists of, again, some specific items. Firstly, you have to generate a stochastic event set most of the time. So the stochastic event set, or simply the stochastic earthquake catalog, what we call, actually gives you the overall idea about the annual seismicity of the country, of the region that you are dealing with to compute the earthquake loss. Besides, each event, each rupture in that catalog essentially will create the ground motion distribution. So essentially for each event in the earthquake catalog, you have to generate ground motion fields for the ground motion intensity metrics of interest. All right, so the ground motion intensity metrics of interest, depending on the vulnerability function you are using, could be peak ground acceleration, peak ground velocity, spectral acceleration at a given vibration period, and so forth. And then you have to compute the annual occurrence or exceedance probabilities of the stochastic events, as well as the ground motion intensity metrics that you populate at each site. Then with this information in hand, with the hazard in hand, then you have to compute the losses of the portfolio in hand by making use of the specific vulnerability functions addressing the capacity or potential of loss for that portfolio. Now, firstly, we compute the ground up loss distributions. I'm not going to go into the details of that kind of terminology, by the way. So ground up loss distribution actually simply means the actual loss faced by the portfolio or the structural system under consideration. And then starting from the ground up loss distributions, then you compute the gross losses or other relevant distributions which make sense to the expert, to the managerial staff in the insurance or reinsurance company. So by saying, for example, gross losses, I mean the losses right after considering the deductibles in the policy statements. And once you compute those different types of losses that are relevant for insurance or reinsurance industry, given a portfolio, then from the exceedance probability curves, which are mainly based on annual exceedance probability curves, you compute specific probabilities for given loss threshold levels, and you compute average annual losses, and then you can also compute the probable maximum losses, as I told you, for their use in insurance and reinsurance company. Now, from this point on, I'm going to walk you through how how an earthquake modeler, in the most fundamental way, compute those sort of loss distributions given a portfolio. I'm going to start from a very simple case. I'm going to talk first, I'm going to consider first a single event and a single asset at a given site. So say that you have a risk at a given site, and close to this risk, there is a fault crossing, and then and then you sort of establish a specific rupture scenario on this fault, that the fault is capable of sort of producing it or rupturing it. So given the rupture scenario, which is this one here in my sketch, with a specific magnitude m at a distance of r kilometers from the risk, you first try to estimate the ground motion distribution at this single location. So as I told you, because of the aleatory nature of the phenomena itself, you're not going to consider a single specific ground motion intensity value, but you will be considering the distribution, which will give you the occurrence probabilities of different levels of intensity metrics of interest at this site. This is why, because I am trying to come up with the loss of a future event, which did not happen. It's going to happen in the future. So for this reason, I'm going to make a good, intelligent estimate of likely occurrences of different intensity metric levels here. So you do it by making use of a ground motion modeling. And then after you compute this distribution, this is your vulnerability. This is your vulnerability function. So the vulnerability function would give you the likely damage, the loss. In our case, it is the monetary loss, as the ground motion intensity metric changes. Now, again, because of the uncertainties which I tried to explain in the previous slide, like the unknowns in the exposure, like the unknowns in the structural or content behavior, or many other things, you are many times you don't consider only the mean damage or change of mean damage as the change in ground motion intensity metric, but you're considering the distribution, the likely levels of the losses given a specific intensity metric value. So you consider the distribution of the damage. So by making use of the distribution of the light intensity matrix and the corresponding damage probabilities, you integrate the losses through this integral from the minimum intensity metric level to maximum intensity metric level to come up with the, say, ground up losses. So now, instead of a single value, through this integral, where if L given M is the conditional loss distribution given as ground motion intensity metric, and then the FIM is the probability density function of the ground motion intensity metric, you come up with the ground up loss distribution, which is this one here, and then you apply the policy conditions to this distribution, and then come up with or calculate the net loss distribution. Now, once you have the net loss distribution, which is essentially the resulting loss distribution, financial loss distribution, right after implementing the policy conditions, then you have to consider, or you have to compute the so-called exceedance probability curves, which is then computation of exceedance probabilities for different threshold levels times the frequency, annual frequency or annual rate of this rupture. So once you have the exceedance probabilities of different loss threshold levels, which is given here with L star, and then multiply it with the annual frequency or annual rate of the rupture considered, you will end up with the exceedance probability curve in terms of rate. Now, this part, for those of you who have taken the basic probability courses, this is the complementary cumulative distribution. Essentially, what you are doing is you're calculating you are multiplying the complementary cumulative probability distribution for the specific case by the rupture frequency of the event scenario that you are considering. Once you have the annual to convert it to annual exceedance probability, just by making a specific assumption like the earthquakes and the corresponding losses and so forth, and as well as the ground motion intensity metrics are Poissonian process. So once you have this annual exceedance rate curve, you can compute the annual exceedance probability curve, which is of interest for the insurance and reinsurance industry. You do it for financial losses. You can also do it for structural damages and so forth, depending on the objective of your, say, project. Now, notes from the previous slide. Now, the computation of loss distribution, which is illustrated in the previous slide, is only for a single event. So this is sort of, everything is relatively easy because it's a single event. And also, it's only for a single risk. Now, most of the time, you know, the seismic source faults in this case can generate many earthquakes with different magnitudes and at different locations within the fault, which I tried to emphasize in the previous slides. So there can be other, and also there can be other faults in the vicinity of the portfolio site. So you have to consider all of these, and because they are capable of triggering different levels of earthquakes, ruptures, and ground motion intensity values. So you have to consider those things in the real life. And besides, we dealt with only a single risk in the previous slide, but it could be a portfolio, and the portfolio could be distributed over a specific region. And in many times, we are running the loss analysis for the entire country. And then there could be different types of structural systems, different types of policy conditions, different types of coverages and so forth. So you have to consider all these cases in the as a whole. So that's why, I mean, that's where the complexity comes into picture. Now you have to repeat that simple calculation that I tried to summarize in the previous slide many times to compute the relevant loss distributions used in the insurance and reinsurance industry. Now, I'm going to start sort of complicating the whole thing, and on the way, the slides that I'm showing you are specific from, I mean, the pictures that I'm showing you are the results of some specific projects that we are dealing in the company. So now I'm going to talk on the single event and multiple assets at multiple sites. Okay, so still we have a single event like the one I'm showing here. All right, so this is one of the scenarios we are we consider for the expected Marmara Sea fault earthquake. All right, now the simulation here presents the variation of ground motion distribution. So say we have a portfolio at multiple sites in the Marmara region, all right? And the colors indicate different percentiles here in terms for the ground motion intensity metric we use, which is peak ground velocity in this case. Now then, and this is essentially, again, the corresponding loss variation. I say loss variation. Why? Because essentially we are calculating or we are computing the distribution, not a specific single value, but the distribution of loss. And again, the change here in the color indicates the different percentiles of loss that we compute for this event. Now, what we do for a given single rupture and a portfolio distributed all over this region, firstly, for that rupture, we have to compute the expected loss value. So this is how you can compute it. The expected loss value given a rupture is actually the loss distribution for each single asset times the loss parameter, taking the integral from zero loss to maximum the boundary case, and also the variance of the loss distribution, again, for each component, for each risk at the portfolio locations. So this is the, again, variance calculation, say formulation for the loss distribution that you have to come up with. Essentially, there is one important point here, which is the rho kj. So the correlation of loss at sites k and j, as the intersite different distance increases, the correlation of loss between the two sites decreases. I'm going to talk on this in the next coming slide. This is an important phenomenon point actually. Now, the loss correlation or the correlation coefficient here, which sort of dominates the dispersion about the mean loss, is composed of two specific parameters or components. The first one is the correlation due to ground motion intensity metric from one side to the other. The ground motion intensities are correlated. Again, if the sites are close to each other, the portfolio sites are close to each other, the correlation between the ground motion intensity metrics is high. And also the other component is the correlation of damage between the two risks. If the two risks have the same types of structural system, For example, if they are close to each other, then most probably they will face or experience a very similar damage level. So this should also be considered in this simple tiny variable, which is not easy to calculate. Anyway, so once you have the expected loss given the rupture scenario, as well as the variance of that loss, then through different assumptions, you can come up with the loss distribution of the entire portfolio for that specific rupture. All right. Now, most of the time, because you're dealing with different types of structural systems in the portfolio, different types of content in the portfolio, as well as the business interruption, different policy conditions, and so forth, you cannot implement this like really very nice theoretical formulations, but you have to use Monte Carlo simulations or Monte Carlo sampling to come up with the loss distribution. Otherwise, it will not be that much easy. So again, this is the variation of ground motion fields, and this is the variation of losses due to that in the portfolio, in the entire portfolio, due to the variation in ground motion fields and other factors. All right. Now, once you the other sort of complication, I'm going to talk a bit more. Now, say that we have resolved the issue for a single event for an entire portfolio exposure. Now we have to repeat the same case for the whole stochastic catalog and for the entire portfolio. Then actually, the previous slide explains this part, the loss exceedance for different threshold levels given the rupture. And now the only thing that you have to do is multiply the annual occurrence of that rupture to come up with the annual occurrence or exceedance rate. This is exceedance, annual exceedance rate of the loss. All right. So this part is quite similar to the one which I explained in the beginning of this sort of subsection in my talk, single risk, single site. Now, this formulation is again quite nice, but if you want to implement it for large portfolios and for say for the entire stochastic earthquake catalog, then again you have to use Monte Carlo simulation. All right. Once you obtain the loss distribution here, annual exceedance rate of loss, again by making use of Poissonian assumption, you can convert the rate into annual exceedance probability, as I am giving you here. So now this is the annual exceedance probability curve, again, which is used by the insurance and reinsurance industry to take decisions. Now, again, this is, I don't know if I can do it, but let me see. Okay, I'm going to stop for a while. So I'm showing you a simulation of our earthquake catalog at TRAP for 1,000 years. Actually, we run our analysis for earthquake catalog periods of 10,000 years, because Turkey is a high seismicity country, so 10,000 years seems to be good enough to address the entire unknowns or uncertainty in the annual seismicity of our country. So, all right. So you see here, as you see here, now almost 1,000 years, you see the North Anatolian Fault, the East Anatolian Fault, the Aegean extension region, the subduction region in the Aegean, in the South Aegean part, the Mediterranean. So this is the Hellenic Arc, the Cyprus Arc, and also we have the earthquakes in the Caucasus region, as well as partly the Iran. So for a good hazard, you should not only consider only the national borders of your country, but you have to consider the effects of earthquakes from a buffer zone outside the country border. All right. Now this is again a simple, two simple illustrations showing how we model the ruptures. So you see for a specific, say, event on a fault, you need to know the geometry of the fault. And once you have the geometry of the fault, for large events, you assume that those large events are they occur on the fault, and for those who are actually cannot be associated with the faults, you have to consider you have to consider them in the background seismicity. And now these small tiny pieces here, they are actually small magnitude events in our catalog. Like this is a snapshot of the catalog. Considering the uncertainty in the variation of strike. So that kind of uncertainty, all in all, you have to consider it in your hazard calculations before coming up with the ground motion intensity distributions at each portfolio site. Now this one here is actually showing you the annual occurrence rate of small magnitude events as distribution. We are considering smoothed graded seismicity in our model to consider the uncertainty in the location and occurrence of small magnitude events, which we call them as background seismicity. All right. Now this is sort of the kitchen for the theoretical kitchen for the computation of loss exceedance curves. Now with the loss exceedance curves, I'm going to explain. I will start explaining more on their nature, the nature of exceedance probability curves or loss exceedance curves. Sorry, yeah. Please remember that they are in annual exceedance probabilities. Now, this is a typical loss exceedance curve. Okay, of course, a sketch here I'm showing you. And what it tells you is the loss threshold levels and their corresponding annual exceedances. All right. Now, L1 L sub 1% here is the amount of loss with 1% annual exceedance probability. All right. So essentially, we at the end of the entire process, we compute this exceedance probability curves for different financial, say, terms like ground up losses, gross losses, or other financial, say, agreement types that are being considered by the industry. And then this is now this is a tabular form. So for each annual exceedance probability, starting from 50%, say, you compute the corresponding loss threshold value. All right. Now, as you would immediately realize, the loss threshold value corresponding to 50% annual exceedance probability will be smaller than the one with 25% exceedance probability, and then the largest one is obviously in this slide will be the loss threshold value corresponding to 0.1% annual exceedance probability. And most of the time, the insurance companies or reinsurance companies, they really are interested in the tail distributions, or the tail values, which I'm going to explain in the next coming slides. There is one thing which I have to point out here. So you see, I'm sorry, yeah. I showed in the slide the annual exceedance probabilities by this way and in this format. Most of the time, and the corresponding losses, of course, most of the time, the insurance or reinsurance industry essentially, they would like to talk with return periods, and actually simply they consider the return periods as the reciprocal of the annual probabilities, which is slightly wrong because essentially the reciprocal of annual frequencies will be the corresponding annual return periods, all right, or return periods. But I mean, the difference between the reciprocal of annual exceedance probability or annual exceedance frequency is very small at the tail portion, which is like the main interest of the insurance and reinsurance industry. So in that sense, we are delivering them the losses for annual exceedance probabilities, and then because in the sector, in the insurance sector or in reinsurance sector, they rather take the reciprocal of it and then call it as return period. We also say this is instead of saying 1% annual probability of exceedance, we just say it is 100 years return period and so forth, which is again a bit of incorrect in terms of return period terminology, because return period essentially should be the reciprocal of annual exceedance rate or frequency, not the annual exceedance probability. But not a big deal, actually, just to emphasize the difference. As I told you in the beginning of my presentation, the exceedance probability curves are actually divided into two main categories, and they have their own implications or implementations in the sector. Now, the first one is called as occurrence exceedance probability, and the second one is called as aggregate exceedance probability. So the annual occurrence exceedance probability gives you the probability that the maximum financial loss in a year exceeds certain amount. So occurrence exceedance essentially will give you the maximum financial losses in a year, the exceedance probability of the maximum financial losses. Whereas the aggregate exceedance probability will give you the aggregate financial loss in a year exceeding a certain amount. All right. So the AEP essentially, the annual exceedance, the aggregate exceedance probability will describe you the aggregated loss distribution, whereas the occurrence exceedance probability will describe you the maximum loss distribution. And both of these different types of distributions have their own uses. I'm going to explain them in the next slides as well. And also there is this probable maximum loss concept. And actually there is no unique definition of probable maximum loss. But most of the time, the PML, which is the abbreviation, will correspond to typically an annual exceedance probability of 0.4% or 0.5% or 1%. So by saying 0.4%, it is like really approximately 250 years return period, and 0.5%, it should be 200 years return period approximately, and 1% is 100 years return period. So PML essentially is there is no unique definition of it, but in the industry, these are the levels of exceedance probabilities which are used to describe the corresponding maximum probable loss values given a portfolio. Now, how do I compute an OEP, occurrence exceedance, or aggregate exceedance probability curve? Here is a very simple example. Now, say that I have I have sampled a stochastic event set for only 4 years of length, time period. And then for the first year, I have a loss in my portfolio of $100. So there's only one single event. And then in the second year, this is a random phenomena. There is no earthquake, there is no rupture for this case. There is no damage inflicted by an earthquake. And then in the third year, there are two events affecting my portfolio with a damage of $500 and $300. And then in the fourth year, there is again a single event and with a damage of $100. All right. Now, if I want to compute the occurrence exceedance probability curve or occurrence exceedance OEP curve simply, then I have to consider the maximum losses. So for the first year, there's only a single event, so the maximum loss is $100. The second year, there is no damage inflicted by or loss inflicted by the earthquakes, so simply zero. And in the third year, it is $500, the maximum of those two. And in the fourth year, it is $100 again. And then now I'm going to start computing the OEP probabilities. So for the $0 loss, $0 loss has exceeded 3 times 1, 2, 3 in 4 years. So it's simply 3 divided by 4 times 100. This is to convert ratio into percentage, 75%. Now, $100 loss has been exceeded once in 4 years. So it is 1/4 times 100 again to convert the ratio into percentage. And then $500 has never been exceeded in 4 years, within 4 years. So the exceedance probability is 0. So this is the loss. Say, I'm going to, oh, no, then I cannot do that. Let me set that. So now I have this PL exceeds L, but this is in terms of occurrence. And now I have the dollar values here, $0, $100, and then $500. And then I'm going to have such a thing. All right. So the probability versus the exceedance probability versus the loss. To compute the AEP, now I have again, sorry, just convert this. Laser point, okay. So now I'm going to consider the aggregated loss. First year, $100. Second year, 0. Third year, 500 plus 300, $800. And then the fourth year, only one event, so $100. Again, the same type of calculation. Now, the only thing is that it's going to be something a bit different. Now, this is going to be 800. And then I'm going to have something like this. So this is now aggregate exceedance probability curve, and this is occurrence exceedance probability curve. Now, you see, one considers the aggregated losses, whereas the other considers the maximum losses and the corresponding distributions. Now, this is quite important, actually. This is very important, actually, because essentially here is the EP curve, either AEP or OEP. And now, if I want to define the tail value at risk, which is actually sort of the critical, one of the critical, say, parameters while given decision, it's the average annual loss above a given annual exceedance probability. And most of the time, the threshold for that this P is 1%. So you just compute sort of the area under this tiny curve, which can really affect the value of the value, because depending on the variation of the tail value here, TVAR will change significantly. All right, and this tail value here is mostly affected by the number of sampling, if you're running Monte Carlo simulations, or the behavior of vulnerabilities, or the type of vulnerability you choose, or the ground motion distribution. So the ground motion modeling, the vulnerability modeling, and as well as the Monte Carlo sampling plays a significant role in the variation of this tiny place, which makes a huge difference in TVAR. Average annual loss ratio, average annual loss, it is actually the expected mean loss that can occur in a given year. And actually the average, but as the name implies, average annual loss, it represents a long-term loss average for either a single risk or for a portfolio of multiple risks. So you just think like something like this. So you have a stochastic earthquake catalog. I'm giving a very simple case with these are the years from 1 to say 10,000 years, and then for each one of it you have from a given distribution loss. X1, X2, X 10,000. So these are say the average losses of each year. So you just take the average of average if you're running Monte Carlo sampling, and then you come up with the average annual loss. Depending on the type of exceedance probability curve you're dealing with, either aggregate loss or occurrence loss, the average annual loss value you compute will differ. So essentially, inherently or by default, aggregate average annual loss will be higher than the occurrence average average annual loss. And it's because this is the aggregated, this is the maximum, and aggregated will always be larger than the maximum in most cases, in case there are multiple events affecting the portfolio in a given year. All right, and again, you can, depending on the problem you're dealing with, or depending on the aim of the project, or depending on the decision that you're going to make, you would either use occurrence average annual loss or aggregate average annual loss. Essentially, if your pricing is based on the maximum loss occurrence, then you will be using occurrence average annual loss. And if your pricing is based on the aggregated losses, then you will be using aggregate average annual loss. So essentially, just think of like you are superhuman, like you're living 10,000 years, and each year or every couple of years, you have witnessed an earthquake, and you know the loss. Essentially, you just sum up those losses and then take the average, and you say, for this given single risk or for this given entire portfolio, per year, on average, you will be having this amount of loss, monetary loss, and that value is being used by the insurance industry for pricing the policies, all right, the premiums. Now, I mean, as loss modeling, and depending on the nature of the work you're dealing with, you sort of make it a bit more complex by considering the aggregated losses or the maximum losses, and that makes a difference between the average annual loss, occurrence average annual loss, and aggregate average annual loss. All right. Now, from this point on, any question? If there are any questions up to this point, I mean, this is just sort of the theoretical part of the presentation. Now I'm going to make some sort of observations about the significance of main model variables on the estimated loss distributions. But if you have any questions about the related to the theoretical part of the talk, I'll be happy to answer. Otherwise, I'll just continue.
So Sina, I think you can continue, and
Oh, okay.
yes, and we can answer the questions
At
after
the
the
end. All right.
partitions.
Okay.
Yes.
So, all right. So now, in the following slide, I'm going to, as I told you, going to discuss. Let me just change it, switch this to laser point. I'm going to discuss the significance of some of the random variables used in loss modeling by making use of the February 6th, 2023 Kahramanmaraş earthquakes. In the presentation, I mean, in the while showing the results or observations, I'm going to make use of the our calculations based on TCIP portfolio. I'm not going to show the actual numbers, but I'm going to show the computed losses in terms of ratios. We are allowed to name TCIP, and we are allowed to sort of use TCIP sort of cases in our presentations, in particular the academic presentations like this one, because essentially Türk Reassurance, our mother company, is the technical operator of TCIP, and TCIP has provided us this type of access in our presentations. So essentially, I'm going to talk on the portfolio granularity, the effect of shear wave velocity distribution, the site conditions, the effect of vulnerability model, and the effect of portfolio location in the calculated portfolio loss distributions. Okay, so before going into the details of our observations about each one of these random variables, I'm going to talk about how we model the rupture scenarios of these duplets, these two major events. I'm not going to give details of the seismological details of Kahramanmaraş earthquakes because it's not the scope of this presentation or talk. And also, I mean, I'm sure that you have heard too much of that in the previous talks by different colleagues from Turkey, from all over the world, related to these two duplets earthquakes. Now, the first one occurred, which occurred at about 4:17 a.m. in the morning, has a magnitude of approximately 7.8, and it ruptured approximately 350 kilometers of, say, Eastern Anatolian fault here, a large segment of Eastern Anatolian fault towards southeast. And the second one actually occurred 9 hours after the first one, with a magnitude of approximately 7.56 and with a rupture length of 150 kilometers. Actually, this is a Sürgü fault, which is the sort of the sub branch of the East Anatolian fault segment. Now, the whole event is captured by approximately 380 strong motion stations, and which we made use of those recordings in our model, by the way. And there are several very large magnitude aftershocks. The well-known ones are the magnitude 6.8, just right after the event, the Nurdağ fault, the Nurdağ aftershock, and magnitude 6.3 Yayladağ earthquakes. All right. Now these are the geometrical properties of each rupture that we use in our model. So essentially, the earthquake itself, the earthquakes themselves, they are known by the phenomenon called as forward directivity phenomenon. I mean, for those of you who are not familiar with this concept, when the rupture front moves toward the side at a velocity close to the shear wave velocity of the surrounding rock, then at those sites we observe big fat pulses, pulse-like signals, and the demand in particular within the pulse period, the spectral demand within the pulse period range increases significantly, so they are quite destructive and demanding type say ground shakes, and in particular the first earthquake. There were many sites subjected to forward directivity effect, which are shown here, the strong motion sites here, which are shown here in inverted triangles, black triangles. And so we considered the forward in our ground motion modeling, the forward directivity model effect modeled by Choi and Young's 2013, which is used in their ground motion predictive model in 2014, Choi and Young's 2014 model. So essentially here, I'm showing you the backward directivity effects for the first event and forward directivity regions, sorry, for the first event and for the second event. As you see here, in the first event, the entire Hatay province, as well as the other small provinces, Osmaniye, and partly a bit of Gaziantep, and also the Adıyaman. They are affected by the forward directivity, and then the large portion of Kahramanmaraş is affected by the backward directivity. When it is backward directivity, the demand is not as much as the region where the forward directivity is prevailing. Nevertheless, I would say if the sites are close to the ruptured fault, essentially the ground motions are still significant. The amplitude of ground motions are still significant, even the region is located at the backward directivity. Now, for the second event here, the forward directivity effects are observed in the northern part of the Kahramanmaraş province, as well as partly Malatya and Adıyaman, whereas the eastern part of the Kahramanmaraş province is affected by the forward directivity, backward directivity. Again, we don't observe big, large pulses in the backward directivity region as in the opposite to the forward directivity region, but still the amplitudes of the ground motions, they can be considerable, in particular, if the sites are close to the rupture. And for these two events, the populated sites or the populated sites or towns, the city centers are close to the ruptured segments. All right. Again, another way of showing the ground motion field distribution for 84 percentile. Recall that we are not calculating single points in terms of ground motion intensity metrics. We're considering the whole distribution, and this is sort of a snapshot of ground motion field distribution for the first event and second event for the Kahramanmaraş province. Yeah, these two for 84 percentile ground motion distribution, the peak ground velocity distribution. And again, I'm not going to go into the details of I'm not going to repeat the same things, but in particular for the Kahramanmaraş province, as you see here, most of the Kahramanmaraş province itself is in the backward directivity, is controlled by the backward directivity. But for the second event here, the forward directivity affected the northern part of the province. Again, the ground motion amplitudes are considerably high. Nonetheless, if it is backward or forward, backward region or forward directivity region. Now, this is something, a complicated way of showing the total loss exceedance probability. Now, just assume that we have two sides, all right? Now, the horizontal axis shows the loss, say, range of the first side given a specific intensity metric value. And then the vertical axis again shows the loss range of the second site given a specific intensity value, only a single value from that distribution. Okay, so the total loss, which is a joint probability distribution here, is the loss coming from the first site and the second site, conditioned on the intensity metric that I'm at this point interested in, IM1 and IM2, times, of course, the occurrence probability of IM1, the intensity metric value at site 1, and the intensity metric value at site 2. All right, so this is the joint probability distribution, how we define basically the joint probability distribution for two sites, with each site having a single asset with a specific, and they are subject to a specific intensity metric value. Now, you can further describe this joint probability density function as the conditional probabilities of IM1, the intensity metric at site 1, and IM2, the intensity metric at site 2, given the shear wave velocity values at site 1 and 2. All right. Now, essentially, the intensity, say, the distribution of ground motion intensities at both sites are correlated, as I tried to emphasize in the very beginning of my presentation, and one of the slides. I mean, you should be considering the correlation in the ground motion, at least in the ground motion distribution. Otherwise, your calculations, the loss calculations, are not going to be accurate, in particular if the sites are closing. All right. Now, if you use the total probability theorem, this is what you have to, I mean, theoretically, this is what you have to calculate. Now, I'm not going to go into details of each one of these terms here. I can provide you the web, I mean, the slides if it is needed. Now, essentially, what this integral here shows that the loss distribution depends on the vulnerability models, the distribution of the vulnerabilities, ground motion intensity, and the site conditions, basically, provided that you know everything about the fault geometry and so on. You know everything about the rest of the things, there is no uncertainty, which is not the case, but this is sort of the simplified version. So the uncertainty in the vulnerability models, the ground motion intensity, and the site conditions, according to this integral, will control your total loss or EP curve. Now, which means now we have two components, two loss modeling components, the vulnerability distribution, the ground motion distribution, and then there is an interaction between these two components with the limitations in the portfolio granularity, geospatial portfolio distribution, as well as the site conditions, because portfolio granularity and geospatial portfolio distribution essentially will be affecting the ground motion intensity metrics, as well as the site condition, the ground motion intensity distributions, as well as the choice of your vulnerability models. In other words, these two components. Okay, so the rest of the slides from this point on will try to explain what are the levels of uncertainty, their contributions to the loss distributions in the calculated loss distributions. So we studied this whole thing systematically. We considered only in this case, we considered only the TCIP portfolio in the Kahramanmaraş province, all right? And then we consider the effect of geospatial distribution of the portfolio, because in the insurance portfolios, you may face the geographic coordinates, well-detailed geographic coordinates of each policy, or you may find that the entire policy, the entire number of policies are lumped in the district centers. Okay, so then the geospatial portfolio distribution can vary from very fine grids, like here 0.025 degrees grids, to all the way to the district centers. So It is something like this, essentially. So you have, say, a region, and then you just say you can. So essentially, if this is the district center, so everything, all the portfolio can be lumped in this district center, or if the granularity of portfolio distribution is well, you can distribute the portfolio in the mesh gridded cells here, okay, with different sizes. So the sizes of the mesh grids in this study changed systematically from 0.025 degrees, 0.1 degrees, and the worst case is the district center. And then the uncertainty in site conditions or variability of site conditions, it depends on the shear wave velocity. The site conditions are generally described in terms of shear wave velocity, and essentially for each site or for the portfolio district center, you can assume a single VS30 value, which is the median VS30 in this case, or you can assume a distribution of shear wave velocity, because you will never be so sure about the variation of ground motion conditions in this tiny grid or in the city center or in the district center. All right. And then again, for each, say, risk in your portfolio, you can assume a mean vulnerability loss versus IM, a mean vulnerability curve, or distribution of vulnerability conditioned on a specific IM value. And then in terms of portfolio granularity, you may have the entire information about the year build and building height of the exposure. And from time to time, you only know about the year build, but you don't know anything about the building height, or in other words, number of stories. Or in some cases, you don't know anything about the year build, but you know about the number of stories. Or in the worst case, you know nothing about the portfolio. I mean, essentially, you don't know anything about the year build, you don't know anything about the number of stories. You just have to make a good guess, or you have to make a sort of generic vulnerability describing the overall distribution or behavior of that portfolio in that region. All right. So in this case, in the worst case, the distribution will be sort of with a lot of scatter, whereas for this case, if you know the year build and building height, the distribution is going to have a lesser dispersion. So we studied each one of these cases systematically one by one by making use of 64 alternative cases. Now I'm going to start giving you the results of our observations. So firstly, I'm going to talk about the significance of geospatial spread of the portfolio. Now, as I told you, if you know the coordinates of the policies in your exposure, you can distribute them to each tiny grid, like 0.025 degrees grids, or 0.005 degrees grids, or 0.1 degrees grids, depending on the number of policies and depending on the coordinate information you have. Some from time to time, you have the exact geocode, or you may have say only the street names and so forth. So then, or you just have the name of the district. So say this is the Kahramanmaraş province. So everything is lumped at the city center of this district, or everything is lumped at the city center of this district. All right. Now here, what I'm going to show is the horizontal axis here is the grid densities. So for a portfolio distributed over 0.025 degrees grids, all the way to district centers. All right. And the vertical axis is the represent the normalized losses for 2 percentile and 98 percentile values, 16 percentile and 84 percentile values, and the median. The median is, in a way, will be not exactly, but sort of you can just consider it as mean, just to make life easier. As you see here, if you lump everything in the centers of the districts, which is this case, then the loss dispersion is significant. Whereas if you have everything well distributed, the distribution, the dispersion in loss estimations or the loss distribution is relatively small. If you are really focusing on the median, it doesn't make a difference. It doesn't make a difference. Either if you lump the whole thing in the district centers, or either you use this type of fine meshed grids, the median results don't change. But recall that it's not the median values most of the time the insurance and the reinsurance industry is after. They're after the tail values, tail. So that's why the median will give you something, will give an idea, and it will be an indicator, but it will not. But if you have a better geospatial distribution, you will have better estimations of the tail. Now, the significance of site conditions, as I told you, essentially, this is sort of confusing because I have been running or modeling ground motion models, developing ground motion models for most of my career, and I know that the site conditions have a significant uncertainty, and it is not easy to really describe the site condition of a specific site if you're not running detailed analyses. If some of you are geotechnical engineers, they would know what I mean by detailed site-specific analyses. But in any case, even if you have very fine mesh gridded cells with a nice, say, portfolio distribution, and this is the worst case, by the way. So you don't know too much of the site conditions, and also everything is lumped at the district centers again. All right. Now, again, I'm going to give you the observations in the same format. The horizontal axis is going to be for different grid densities, all the way from the finest grid density to the district center. Everything is lumped out in the district center, and then the vertical axis is the normalized loss. Anyway, so now there are two vertical bars here. The first one is when you are the black one, the black dashed line, when you are using distribution of VS30, so you consider the entire variability in the site conditions, and then you only use the median shear wave velocity. All right. Now, what this says again, if you are only dealing with the median losses or the average losses, in a way, this much of complication doesn't make a huge difference. Okay, this much of complication doesn't make a huge difference. Essentially, the median loss is not that much sensitive, whether you consider the site condition variability or you just consider the median VS30 value, or you distribute your portfolio over fine grid cells, or you distribute everything, you just lump everything in the district center. On the other hand, again, the distributions in terms of percentile values, it makes a difference. Now, if you are only considering the median site conditions, then the range of uncertainty or the range of distribution is narrower than the one, obviously, when you consider the variability of VS30 or the site conditions. In my opinion, I mean, this is my personal point of view. I mean, disregarding the variation in VS30, if you're dealing really with the tail values, it may affect your results. And as I told you in the beginning of this, while I start explaining this slide here, I mean, if you have not done detailed site investigations, site explorations in terms of site conditions, there will be always some level of uncertainty in your results, and then it would be better to consider the uncertainty in the or variation in the site conditions. In the worst case, it is really disregarding entirely the site conditions. And from my personal experience, the loss even gets halved if you disregard the site conditions in your loss calculations. Now, significance of distribution or variability in vulnerabilities. Now, what I refer to from this, title is that now if you disregard the variability in the vulnerability, you only consider the mean. But if you consider the mean damage ratio for a given, say, peak ground velocity, this is sort of this cumulative distribution of the damage. And then this is, if you consider the distribution of variability in ground vulnerability, then which means you're considering the entire variability in for a given peak ground velocity value. So it means the damage could have a non-existence probability of 40%, 0.2 damage ratio as a non-existence probability of 0.4%, and then 0.8 damage ratio as a non-existence probability of, say, almost 90%, or existence probability of 10%. And for a given PGV value, this range can happen. So you're considering the whole damage range for a given peak ground velocity value when you consider the variability in the vulnerability. And essentially, again, the same type of plots here. The horizontal axis show the different cases for grid densities from finest to the coarsest one. And then for each case now, there are again two vertical bars. The red dashed vertical bar indicates mean damage ratio, which means without considering the variation of damage ratio. And then the black dashed lines here indicate the loss calculations consider both the variability in the damage ratio as well as the variability of VS30. Now, as you see here, for the fine-tuned case, the variation is not much different, but as the grid sizes get coarser, there is a huge dispersion. The dispersion increases, and interestingly, the level of loss distribution in terms of tails, without considering and by considering the uncertainty in damage ratio on VS30, the tail values here of these two loss distributions, even by considering the mean damage ratio or by considering the entire range of uncertainty in damage ratio, as well as the uncertainty or variability in VS30, they're almost the same for each case. And I'll come to this point later. Now, this is something important, portfolio granularity. Now, in this case, you see you have 4 different cases. In the first case, case A, you know everything about the building portfolio, the exposure, the year built, building height, and everything. And in case B, you only know the year built, and then in case C, you only know the number of stories, and in case D, you know nothing about the exposure. So here you have to consider a generic vulnerability, whereas for this case, you can consider a vulnerability model for each type of building. Like, for example, those that were built before, in our case, in Turkey, before 1975, and say low rise between 1976, 1999, and low rise, and then right after 1999, from 2000 to 2018, again low rise. This could be mid rise, and then high rise and tall buildings, and then from 2018 and after. Here we're considering only before 75, between 76, 99, and after 2000. Anyway, so for these 4 cases, and this is wrong. It's not this is portfolio granularity. So as you see here, here again we have 2 different vertical bars here. The first one is the black one is when the uncertainty in damage ratio and VS30 are included, whereas the red one here is when the mean vulnerability and median VS30 is considered. And as you see here, depending on the assumptions you make and depending on the portfolio granularity, the variation of loss is significant, which indicates simply that the portfolio granularity it significantly affects the loss distributions. So just to go over the overall observations in this case, the median loss, again, in a portfolio, it is insensitive to the consideration of variability in damage characteristics of the buildings. In other words, the vulnerabilities considered in the model, the location uncertainty of the buildings, in other words, the geospatial portfolio distribution, or consideration of variability in site conditions. If you're really focusing on the median loss only. But these parameters really make a difference when you are dealing with the loss distributions, in particular the tail losses, and the common observation from all of these case studies is that the dispersion of loss distribution is larger when we lump everything at the district centers. Okay, now in all, the portfolio granularity makes a huge impact on the loss distribution, makes a huge impact on the computed loss distribution. So these are the main 3, say, outcomes of the entire systematic case studies that I tried to summarize you in the previous slides. But then there is one important question. Now, what else? So besides the portfolio granularity, in between those different random variables, control more on the loss distribution, or the accuracy of loss distribution, or let's say the nature of loss distribution. So in this case, we have to run the variance composition. We decompose the variance. Now, I'm going to explain you what it means. So essentially, so this is now so you have a loss calculated for a specific event. Say we're talking about events, a specific event here. Now, the variance of the loss distribution, this one, is decomposed into 2 components. The first one is the expectation of variance of losses conditioned on specific random variables, and then the variance of the expected values of losses conditioned on that specific random variable. Now here, in our case, we choose the random variables to vary, to decompose the variance as the portfolio granularity parameters, the year built, building height or number of stories, and both the year built and the building height. Then we compute the loss distributions and decompose the variances by considering and disregarding the variability in the vulnerability and site conditions, which are described by VS30, characterized by VS30. So now at the end of this, okay, so this is something like that. So now we have, this one is year built, year building height, and then the third one is both year built and building height. So for each case, these are the conditional losses for each case here, their distributions. And then we're calculating the expected losses conditioned on each one of these random variables, or the variance of the expected losses, expectation of conditional losses conditioned on these random variables. All right, and I mean, I'm going to show you the results, but beforehand, I will just indicate that the expectation of variance of conditional losses conditioned on these random variables will always be larger than the variance of expectations of the loss distributions conditioned on that random variables, which are year built, building height, and both year built and building height, which means actually the dispersion of conditioning random variable is dominates the loss distribution, or the dispersion of the conditional random variable dominates the loss distribution. So this is again indicating that the tail distribution is quite critical. Anyway, so now these are the results, overall results. We ran the analysis for two specific cases. The worst case, portfolio all at district centers, and then portfolio distributed at 0.025 degrees grids. And then we considered the uncertainty as I told you. So this is X1, year built result. This is X2, story height is unknown. And then this is year built and story height, they are known. All right. Now this is X3. All right. Now we'll see whether these random variables really affect these distributions, as well as the shutting off and then turning on these uncertainties in the vulnerabilities and site conditions really affect the distributions. Now, this is a very limited study, and I mean, we should be going more and more into this, say, type of decomposition of variance. But what it shows here, just to save time, is that if you know a bit more, if you are certain a bit more on the site conditions, the distribution, the loss, the uncertainty or the dispersion in the computed loss distribution will be smaller, will become smaller, which means the knowing site conditions will give you more confidence in the computed loss distributions rather than the unknowns in the vulnerabilities. This could be specific to the TCIP portfolio, but this is the current observation we have in hand. Now, I'm almost completing my presentation. I'm sorry for Erdem Bey for taking too much of his time, actually. Now, the last component I'm coming here is that the significance of correlation in loss. This is one of the formulations that I gave in the very beginning of my very beginning of my talk. So I was just mentioning about this correlation coefficient, and I just said it is composed of ground motion and structural damage, or damage simply, because you could be looking at the content damage as well. Anyway, so I mean, there are various studies related to correlation of ground motion, whereas the damage correlation is really a sort of quite unknown, because there is not too much data related to damage data to run a correlation for damage. All right, but after Kahramanmaraş earthquakes, we did have that kind of data in hand, and we started to compute this type of correlation, the damage correlation, considering the proximity of the sites as well as the proximity of the risks. Now, here is a very quick results I'm showing here. So if you really, so the loss results for two buildings, building 1 and building 2, at two specific sites, when you consider the correlation of both damage and ground motion. Now, this one here is when you consider only the correlation of damage, but disregard ground motion. And this one is the losses when you completely disregard the correlation. Both the structural and the loss correlation as well as the ground motion correlation. Now, these are the representative distributions from this Monte Carlo simulation. As you see here, when you disregard the whole correlation, which is this one, you end up with smaller values of losses with respect to the red one, which consider both the ground motion and damage correlation. Now, there are several papers showing this type of results, but for the first time after Kahramanmaraş earthquakes, we had the opportunity to run, and we were still working on it, but we had the opportunity to run damage correlation functions by making use of the observed data, as well as we had the opportunity to see how that kind of consideration in the loss modeling will give you a level of difference, a realistic level of difference in the computed losses. Well, thank you very much. I took it a bit long, but I hope that the overall view that I try to give here is useful for the audience to understand the meaning, the significance of earthquake loss modeling for insurance and reinsurance portfolios. Thank you.
Thank you very much, Sinan. And I think now, Erdem, if you want to go directly on, and then we will take all questions at the end.
Okay. Let me just share my screen. Okay. So, greetings everybody, and I'll just try to make an attempt for complementing Professor Akar's heavy and very informative presentation. I'll try to provide 4 use cases where the insurers and reinsurers, at least in Turkey, at least at the current state of the industry, where we utilize the outputs of the earthquake model. So this is an illustration from a book called Disaster Insurance Reimagined from Jarzabkowski et al. And I think it's very informative in the sense that it talks about a paradox of knowledge. Having too little knowledge against disasters renders insurance and reinsurance impossible, as well as, hypothetically speaking, of course, having too much knowledge would leave no merit in insuring the risks, because the risk would be equal to the price, or even the price would be higher than the risk. So these are hypothetical asymptotes on the far left-hand side and right-hand side. So the possibility of insurability lies in the equilibrium of knowledge against disasters, which are infrequent and also highly severe events. So having knowledge about the hazard site for Turkey is a top one. As you can see, this is our the current version of our National Seismic Hazard Map, of which Professor Akkar was also the project executive. And as you can see, most of our country is earthquake prone. And not only this, aside from the hazard side, on the risk side, we have a lot of complexities. This is a historical view on the earthquake caused in Turkey, and I can see 8 iterations, and there is quite some heterogeneity. So aside from the uncertainties coming from the inherent nature of the hazard and risk vulnerability part of the problem, there is also many uncertainties coming from the quality of data and other facets of the problem at hand. Now, I'm going to talk about 4 use cases, and I promise this is going to be quick. And I'm going to talk about 4 use cases that we have been utilizing both in our parent company, Türk Restaurants, and also in the property and casualty insurance industry of Turkey as well. First one is right-hand side, the upper one, the stochastic modeling. This is what we call, and the AEP curves and the OEP curves that Professor Akkar has been mentioning is the output of stochastic modeling. And second one is taking into account some expected major events, scenario-based modeling and stress testing, especially in our case for Marmara region, is another use case. Now, single risk modeling, I mean, modeling for single risks or risk portfolios at a single location has been a use case for some time, especially in the industrial and commercial risks in insurance underwriting, and also post-cat analysis. The analysis that we provide after the event is the fourth one. The stochastic modeling, there was a question I saw about the regulatory authority as well. The stochastic modeling is the main model output that the insurers and reinsurers have been utilizing not only in Turkey but across the globe in the current state of insurance and reinsurance industry. In Turkey, we have a limitation for the insurers and also the reinsurer, how much retention, how much of the risk that they can carry compared to their own assets. And the limit is based on the output of the stochastic models, and especially 250 years return period, or is it 99.8? Yeah, 99.8 value at risk level. And also there is the scenario-based modeling and stress testing. Stress testing has been in our agenda for 2 years now, especially after the Kahramanmaraş earthquakes. There has been a reawakening about the seismic gap in the Marmara region, and the regulatory authority demanded the reinsurers to provide provide the stress test results to closely observe the solvency of the readiness, preparedness of the insurance industry for such a great event. And we have now 4 different scenarios for an expected Marmara earthquake, and this is not the only case. Also, we provide other studies for specific regions that are high seismically active, like Izmir, and also some other locations as well. Single risk modeling is a rather new use case, and we for some time have been advocating for a shift left for the insurers to utilize models not only for the yearly planning of the reinsurance renewals, but they should embed modeling efforts and model outputs in their day-to-day decision-making processes. And in other words, they should embed modeling into their risk selection and pricing routines in their underwriting processes. And single risk modeling is our solution and offering, and it has been used for some time at the moment. And also the post-cat analysis, of course, after a major event, just like what happened in Kahramanmaraş, 6th of February 2023, there is a fog of war and very little communication with the affected region. And you have to make, as insurers as well, you have to make quick decisions in terms of logistics, cash flow, communications with your stakeholders. So there is a time value for an educated estimation, which is the post-cat analysis of a model. And we have been providing that for events that are above a certain magnitude. So to sum up quickly, the earthquake loss modeling has been used for determining the capacity need for reinsurance and also the risk transfers of the reinsurers as well, for cash flow and impact on P&L and operational planning after large earthquakes. They have been used for pricing the technical earthquake policy premiums. And also there has been some use cases for non-traditional risk transfer methods in the insurance industry. And but after all, this boils down to a single fact that one of the definitions of risk is deviation from the expected value. So dealing with uncertainty, you have to have an expected value. And for catastrophes or disasters, for the events that are infrequent in nature and also high in severity, the expected value is provided by models and modelers to the decision makers in insurance and reinsurance bodies. And thank you for listening to me.
Thank you.
Thank you very much, Erdem. There are quite a number of questions. And first of all, thank you very much to both speakers for a very in-depth and revealing presentation. It's very rare to have such clear analytical presentation from insurers. So the understanding of the model, it's a very added value of this talk, definitely. There are quite a number of questions. So maybe we can go directly to somebody that is asking, can you suggest a method to estimate the losses once I obtain the probability of damage of a structure?
Essentially, Dina, if you know the corresponding, consequence value, so say you have a damage probability of say 50%, 60%, and if you know the corresponding consequence value, then you can really convert that damage to a monetary value, which is quite difficult in many cases. So firstly, you have to understand the level of different damage states given ground motion values, and then you have to make use of a consequence model which converts damage to monetary value, and then by considering the occurrence probability of those damage probabilities, damage state probabilities with the corresponding monetary values, you can come up with a compound vulnerability model. And if you do it for multiple, say, analytical model, you will come up with a dispersion of the vulnerability model. So essentially, the way how Odai suggested sounds nice, but very difficult to obtain.
Thank you. So, and then there is a question from Odai Yabari. It says that you mentioned single event, single risk, that this was very much at the beginning of your talk. And he would like to know what do you consider risks such as fire and flooding as follow-up and linked to earthquakes, so consequence of the main event, and if so, how do you incorporate those risks?
Most of the time, the fires following the earthquakes come into picture. We are working on that model, and I hope we will be adding it, integrating it to our model by the end of this year. So fire following earthquakes, not floods triggered by earthquakes, which seem to be rare, or which I don't know, but the flood events also, we will be adding it to our, as a peril, we will be adding it to our model in the next year. We have already started working on this.
Yes, I suppose a flood could be triggered by a landslide, which would
exactly
flood, but
flood can,
and the landslide could have been triggered by the earthquake. But yes, it's a chain of event, which is, I doubt that an insurer would be interested in insuring against, unless it's in a new, some very specific asset, such a nuclear reactor or something like that. Yes, thank you. And then we have, another question. How do you categorize earthquake records into near field and far field motion? I think, and what are the key characteristics used to differentiate them? This, I think, it's answered. Well, you can answer it quickly, but I mean, it's something that can be found in books.
Exactly, it's a text type definition. I mean, essentially, if the ground motion is controlled by forward reactivity, essentially the rupture front moves toward the side at a velocity close to the shear wave velocity of the rock, surrounding rock, actually. So it's when there is such a case at the sites, at the recording, the ground motion recording have very large pulses, and those pulses essentially increase the demand in the vicinity of the pulse period. So there is, there are different models addressing this issue, and we used in our case, we used Choi and Young's, a well-known model, well-established model, to address the forward reactivity effects in the model, in the ground motion model.
So
the backward reactivity is just the opposite of it. It's just
Joshua Di Masaka is asking, well, first of all, many thanks for this amazing talk, and I agree, really amazing. He says, I'm interested to hear more about the assumptions behind the mathematical derivation for the variability of the length of the rupture I, with emphasis on the correlation term rho. I think you discussed this a bit at the end. Maybe this question was before you discussed it. Yes.
Yeah, I mean, essentially, I can email it because this is, it may take a while to explain and discuss all these. So if he can send me an email.
Yes. So Joshua,
and I can answer to him.
You are encouraged to get into correspondence. an anonymous attendee would like some more clarification on the difference between OEP and AEP.
Yeah, occurrence exceedance, and
Yes.
actually the difference is, I mean, in a way quite simple. OEP deals with the exceedance probabilities of the maximum loss, whereas the AEP, aggregated exceedance probability, deals with the exceedance probability of the aggregated losses. So say in a given year, there is only a single event.
Yes.
By definition, AEP and OEP probabilities will be the same. But if the portfolio is exposed to two or multiple events in a given year, AEP will just simply add the losses, aggregate the losses, and then compute the exceedance probabilities, whereas OEP will seek for the maximum loss among those and the exceedance of that loss for different threshold values. That's
Yes,
I would say the
very
simplest
clear
way of explaining it.
explanation. And then Joshua again was asking whether it's possible to have some of the data that you are illustrated in the examples, and if these are available for research or academic purposes.
Not that I know. I mean, there are some data available, public open, but the ones that I'm using are from TCIP, and we are, as the subsidiary company of Turk Restaurants, are allowed to use them for developing models for TCIP, but not for public use.
And then there is a message from our common friend Mustafa Erdik.
Ah, Mustafa Hoca is he around? Okay.
Yes, he says that he doesn't have any questions, but he would like to express his appreciation for both
Thank you
of
very
your
much,
presentation.
Professor Erdik. Thank you very much, Professor.
Exactly. Thank you, Professor Erdik, for listening to us in the first
Yeah.
place.
Thank you very much.
And Amir Orumiye, I wonder if Professor Akan can explain on the procedure of damage correlation calculation as if there is a physical interpretation of the correlation. Yes, so
Yeah.
I think your last slides, which was quite interesting as well. Yes.
Yeah, I mean, if Amir wants to know more, we can discuss it via email, because I mean it may take a long, say, sort of discussion here, and we can do it by exchanging emails.
There are many other questions. How do you disaggregate and aggregate exposure? A stochastic risk analysis based on a 10,000 year simulation was referenced. That's true. In the context of a scenario-based analysis, is there a generally accepted or sufficient number of ground motion field that could be considered?
Depending on the distribution of the portfolio, actually, depending on the distribution of the portfolio type of the structures that they're dealing. I mean, as far as I know, if you're running Monte Carlo sampling, which is the case in many times, then you can use, I mean, hundreds of simulations to come up with an entire distribution with a reliable mean value. And so, because the tails are becoming much, I mean, significantly critical if you only run once the Monte Carlo sampling, or twice, but you have to do it maybe 50 times, 100 times at least.
And in fact, a related question is, when using Monte Carlo simulation, taking into account multiple events at the same location, and considering our distributed building pool, the same buildings may go beyond repair or considerable damage many times, and the loss may go beyond the value manifold. Please elaborate on the issue and give your suggestion, and happy Nowruz.
Happy Nowruz. Okay. I know Professor Ashtiani as well. It
Yes.
would be nice. I mean, I know Babak Mansouri. It would be nice if we can have a long-term discussion via email, because this may take a while. I mean, there are things that before diving into this discussion, you have to make some certain assumptions about a theoretical case, and then from that point on, you can iterate on this question, but it may take a bit long.
I think that this more or less concludes yes, please.
Please,
Sina.
Dina, if any questions that I I encourage the ones to write me an email. Just send me an email for those whom I couldn't answer their questions clearly.
Mhm.
We can discuss them via email, and I'm sure they will enlighten me, and I will try to transfer my knowledge about what I know.
Thank you very much, Sinan, to make yourself available for this. This is really how our community of knowledge wants to develop. So please, all audience that has more questions for the excellent presentation that we have listened to today, which has exactly raised more questions that we can answer in this space. Write directly to Professor Sinan Akkar at his email address is on the invitation.
They can reach me easily from LinkedIn or
Yes,
via my company email.
exactly. Thank you again. I think with this, we want to thank again both Sinan and Erdem for an excellent afternoon of very revealing understanding of how CAP models are developed. And we look forward to more of this discussion. Thanks, and have a nice evening to also all our audience for always the quite interesting questions that come with it.
It's our pleasure. Thank you very much, Dina, for
Thank you.
providing this
Thank
opportunity.
you.
Thank you. Thank you.
Bye
Thank
bye.
you.
Thank you.
Bye-bye.
Goodbye.